Can you tell which of these equations is wrong just by looking at them? I can't say which are right, but some are definitely wrong. Consider this example. It is, supposedly, the tensile strength of a brittle material with a crack of length A. Gamma is the surface tension and E is the Young modulus of the material. The dimensions of each quantity are as follows. The tensile strength is a stress, so it has dimensions of force per length squared. Here, the square brackets mean the dimensions of a given quantity. Gamma is a surface tension, so it has units of stress times length, meaning its dimensions are force per length. E, the Young modulus, has dimensions of stress, and the crack length is of course a length. Substituting into our equation the dimensions of each quantity, we can see that it is not dimensionally consistent, so it can't be true. We found this out just by looking at the dimensions of the quantities involved, not the quantities themselves. This is great and all, but could we have found the correct equation just by looking at the dimensions? You must be thinking to yourself, of course not. But what if I told you that we could get very close? Let me show you. First things first, we are going to consider exactly the same quantities as the ones relevant to determine the tensile strength of a brittle material with a crack of length A. You must be asking yourself, why these quantities in particular? Maybe there's a quantity missing, or maybe one of these quantities won't influence the tensile strength of the material. We will talk about that later in the video. For now, just stick with me. We are looking for a relationship between all these quantities. We can write it implicitly in a very general way as the zero of an unknown function of all the quantities considered. There is an enormous quantity of functions we could consider. But remember our insight about dimensions. A relationship between all these quantities must be dimensionally consistent. That said, we can reformulate our problem in a much simpler way. We will just consider functions of dimensionless groups built from the quantities we are interested in. This will make our relationship automatically dimensionally consistent. Take for example the ratio between the tensile strength and the Young modulus. They both have dimensions of stress, so their ratio will be dimensionless. The same can be said for the ratio between the surface tension divided by the crack length and the Young modulus. As such, we only need to look at functions of these two dimensionless quantities or groups. Now, assuming that this function only has one zero, we can write an equation explicitly for the tensile strength. Sometimes this can't be done. This happens, for example, when there is no closed form expression for the quantity we are interested in. In this case, we will assume that there is. So we are still missing a function, right? We could, for example, run a set of experiments and determine it experimentally. In this case, we would probably find a square root function. And lo and behold, this is exactly the estimate found by Griffith for the tensile strength of a brittle material with a crack using more advanced methods than our own. At this point, I'm sure you have understood some of the power of dimensional analysis. But I'm also sure you've noticed that I left some loose ends. Like, what quantities should we consider? Is there any way to improve our choice of the final missing function? Before we proceed, maybe it is a good idea to formalize a bit what we did. We found two independent dimensionless quantities or groups by what's called inspection, meaning we found our two dimensionless quantities just by looking at their dimensions and thinking a bit. In general, how many independent groups can we find? To answer this question, we must first introduce the idea of an effective dimension. Getting back to our example, our two effective dimensions are force and length. That said, the so-called Buckingham's pi theorem will guarantee that there will be n minus j dimensionless groups, where n is the number of quantities with dimensions and j is the number of effective dimensions. So, in our example, we would expect two dimensionless groups. That is exactly what we found. Now, let's look at two simple examples to see how we can use our physical intuition to improve our results coming from dimensional analysis. In our first example, we are asking what is the deflection at the end of a cantilever beam when we apply a force at its free end. The relationship we are looking for is between the deflection, the force, the length of the beam, and the Young modulus. I think that the inclusion of the deflection, the force, and the length of the beam are fairly straightforward, considering the Young modulus of the material may not be as obvious. but the Young modulus of a material is a measure of its stiffness. As with a common spring, the stiffer the material, the smaller the deflection will be for the same applied force. By inspection, we can easily find these two-dimensional groups. Using the same argument as before, we can write an explicit expression for the deflection of the beam. So here it comes our first physical assumption. If the deformation of the beam is not too large, we can assume that there will be a proportional relationship between the force and the deflection. If you think about it, that's exactly what we find in a common linear spring. Making use of our hypothesis, we can find a very simple expression for the deflection, where pi is an unknown dimensionless quantity. And is this formula correct? Let's check using our physical intuition. The deflection is larger the larger the force. This makes sense. And the stiffer the material, the smaller the deflection. This also makes sense. However, the longer the beam, the smaller the deflection. This makes no sense. Something is missing. Perhaps it is a good idea to just look at the differential equation we would have to solve to find the deflection. Introducing some further assumptions regarding the thickness of the beam, coinciding with the so-called Euler-Bernoulli beam theory, we have the following differential equation, where W and F are the functions describing the deflection and the force along the whole beam. They have already entered our analysis as delta and F, but there is a new character we had not considered. I is the second moment of area of the beam's cross-section. It must be considered because when bending a beam, the cross-sections will rotate, and the higher the second moment of area, the harder they are to rotate. The second moment of area has dimensions of length to the power of 4. So we can introduce a dimensionless group as I divided by the length to the power of 4. Since we can see from the differential equation that the Young modulus and the second moment of area of the cross-section appear together, this must also happen in our case. Now our expression predicts a larger deflection for longer beams. This makes sense. This, for example, is the complete result for a beam with a rectangular cross-section. We got almost there and no need to solve a differential equation. For our second problem, let's look at the system of two bodies orbiting each other, the Earth and the Moon, or the Earth and the Sun. Both bodies have mass m1 and m2, and they orbit each other at a characteristic distance. Our goal is to understand how these quantities are related to the orbital period, that is, the time it takes for the bodies to return to their original positions. These quantities may at first seem sufficient to address our problem, but keep in mind that gravity is the main driver of this interaction, and we have said nothing about it. To illustrate this, consider Newton's law of gravitation. The constant g appearing in the formula is the so-called universal gravitational constant, and it has the following dimensions. I'm sure you agree it makes sense to include it in our analysis. We proceed again by inspection. We expect to find two independent dimensionless groups, since there are 5 quantities with dimensions and 3 effective dimensions. Remember Buckingham's pi theorem. The first group is self-evident. The ratio between the masses of the two bodies is of course dimensionless. The second group is also easy to find because, except for the universal gravitational constant, all the other quantities only have one dimension. We follow exactly the same procedure and we find this formula. While this may not appear to be much, it is a remarkable result. It tells us that the square of the orbital period is proportional to the cube of the characteristic distance between the two bodies. This is Kepler's third law. But using our physical intuition, we can still go further. Since the orbital period of the two bodies does not depend on which body we call number 1 and number 2, we still have a symmetry to explore. What I just said can be written as the following functional equation. One possible solution for this functional equation is as follows, where c is a dimensionless constant. So we can finally write this wonderful expression. Using dimensional analysis and a bit of physical intuition, we got very close to the correct solution, and we didn't need to run a numerical simulation or even solve a differential equation. I think we got a pretty good idea of the power of dimensional analysis. In the next video, we will look at scale models and the classification of problems using dimensional analysis. Stay tuned!